Welcome to our YouTube channel. If you are visiting us for the first time, please remember to subscribe for more of Igcse STEM content. In this video, we are looking at construction of ionic equations. By the end of this lesson, you will be able to ionize aqueous ionic compounds and use this knowledge to construct net ionic equations. To begin with, let us define an ionic equation. An ionic equation is a chemical equation in which the formula of dissolved aqueous solutions are written as individual ions. Therefore, it is very important to always know and show the state symbols of all reacting species in every reaction. State symbols are simply letters that are used to show the physical state of substances in the equation. State symbols are placed in brackets after in the name or formula of each substance in the equation. Let's look at the four state symbols that we have. So we have gas or vapor, which means the same thing. The symbol is small letter g, which should be put at the end of every symbol as a subscript. We have liquid, where we can use L. Again, you write it in brackets and you put it at the end of every symbol of each element or compound. Then we also have solid, or it is known as precipitate, which can be abbreviated as PPT. This one is solid. So in case in the equation you find something said a precipitate, just know that they are talking about a solid. Then we also have the aqueous solution, which is our bone of contention with regards to construction of net ionic equation, because this is what we should be looking out for. When something has got aqueous or AQ at the end of it, then it means that that particular thing should be split. So just to do this, let's look at how do we ionize. So what is meant by dissociation of ionic compounds? Let me just mention that in this context, ionization or dissociation can be loosely referred to as ionization, because a compound is splitting to form individual ions. Hence, ionization also qualifies here. Let's just define. Dissociation is the separation of an ionic compound into its cations and anions, and it occurs when a solid ionic compound dissolves. So you can dissolve it in water or in any other appropriate solvent. The water is the most common one. So we are saying the process results into the formation of ions, hence can sometimes be called ionization in this context. Let's look at a few examples on what we are talking about. Let's look at sodium chloride here. So sodium chloride, we know that it is made up of sodium and also chlorine that have bonded together to form sodium chloride. Now we know that sodium is coming from a metal and chlorine is a non-metal. Hence, when this separates, this will go back to cation and this one will go back to anion. Now a cation is simply a positively charged ion and the anion is simply a negatively charged anion. So this sodium chloride, when it is dissolved in water, it is going to separate into sodium and chlorine, but there is also something that it will gain. It's going to gain the metal part will gain a positive charge and the non-metal part will gain a negative charge. Same applies to HCl. Now, just a little bit of the background in case someone has forgotten. Remember, when we are making the formula for sodium chloride, you wrote Na with a valence of 1 and then Cl with a valence of 1. Then remember there was a swapping here, so that's how you came up with the NaCl. So when we say we are ionizing this one, it's more like we are going back to where we started from. So back from here, we go back here, and then the only thing that we're going to add is to the metal, it has a valence of 1. So to this valence, we're going to add a plus. So metals, they gain a plus, and the non-metals, they gain a minus. Now also remember that 1 is an invisible coefficient, so we can ignore it. Hence, that's why we just write in Na plus and Cl minus. Same thing will apply to HCl. It will separate into H plus and Cl minus. Also sodium hydroxide into Na plus and OH. Now this is a radical here. That's why it is being separated as OH. So this is a little bit of a background that you need in order for you to understand ionic equations. Understand the rules about dissociation. So dissociation of aqueous compounds, here I've just decided to put the rules so that you can pause the video, go through the rules and try to do the examples that are given here. So let me try to go through the examples just using the rules that are here. So I'll be following these rules 1 to 5. If you can follow these as well, you'll be able to get exactly what we are talking about. So the first step is for you to look at the ionic compound. You have to ask yourself a question. Am I supposed to dissociate this one or not? And your answer lies in, does it have AQ at the end? So for example, this one has AQ. So the fact that it has AQ, it means I can dissociate. So after that, then I'll go to the second step where I ask myself, which one is the metal part and which one is the non-metal part? So we can do come up with an equation here. So the first thing we can see, barium is the metal here. So we write barium, Ba, and also barium is found in group 2. Therefore, it has a valence of 2. So you are going to write the species on their own, the metal part on its own and the non-metal part on its own. So Ba, we write it. Then what will remain on the other side is the NO3. That is the one that you are going to write. Then you're going to write the valences for these species. Ba is found in group 2, therefore it has the valence of 2. NO3 is a radical which has got a valence of 1. Then after that, so you can even put the symbols here, AQ, you put it in brackets. Also this side, you put your AQ in brackets as well. So AQ, and then there's a plus here. So you've separated what was like this, you separate it into that one. But you are not yet done. We go to another step which says you need to put a plus to the metal, to the valence of the metal, and a minus to the valence of the non-metal. Now, this valence, this charge, you can either put it in front or behind. So I'll put the plus here to give me 2 plus, and then I'll also put the minus here. Now, I could have put it 1 minus, or the way I've written it, it's you to decide. So after you put that, then there's something that you also check. You look out for any numbers that are there other than valences. For example, we have a 2 here, which is written as a subscript. So what happens is this 2, you don't ignore it. This 2, it is going to go to the front of that particular species to which it is attached. So this 2 is just attached to NO3. Therefore, it will go to the front of NO3, not the front of everything, but just the front of NO3. So this 2 is supposed to be in front there. Okay, that's what it is. That's what this one says. Remember to move any subscript number behind every species to the front of that particular species. Okay, that particular species, not the whole thing, but that particular one. So after we separated the 2, we had to put it in front here. And this is how you write. And please take note that if you want this one, you can just write it as 2NO3 negative, because 1 is an invisible coefficient, so we can ignore it and we just write it like that. All right, there is another example here, the second one, which we have done in the previous one. So you just ask yourself, how do I separate this one? Okay, I have Na and then I have OH. So you need to have the knowledge of radicals if you are to successfully do these things. So here again, if we are writing the equation, we're going to have our Na, and then on the other side, we're going to have our OH. So we have our Na and our OH. The valence of sodium is 1. The valence of the hydroxide is also 1. Sodium is a metal, so we're going to put a plus, and then here we're going to put a minus. So we write plus here, and that is how you write, because it doesn't have any other numbers. Let's look at HCl. HCl will also be the same. We have the H plus, okay, plus the Cl minus. Remember to be putting your state symbols there. Okay, you put your state symbol here. You also put your state symbol here, because state symbols are very important here. Now, the valence of hydrogen is 1, that's why I've just said plus, and the valence of chlorine, which is a nonmetal, is 1, that's why I've just put minus. 1 is an invisible coefficient. Now, let's look at this one. This one is BaSO4S. So the state symbol here is a solid. Therefore, this one cannot be associated. It cannot be split. Also, H2O is liquid, so it cannot be what? Dissociated, because these are not aqueous. So in conclusion, on how to dissociate ionic compounds, we are saying look out for the aqueous symbol. If something is aqueous, then it means you can split. If it's not aqueous, it means you can't split. Please take note of that. This topic is going to be very important as you progress through your chemistry course. All right, just so you refresh your minds, you can pause this video and look at some common ions and their formulas. As you are looking at these ones, please notice that radicals, they are also of two charges. There are radicals that have got a positive charge. There are radicals that have got a negative charge. So you should be able to be familiar with these radicals. That's when you can be successful in the dissociation process. Now that we understand this, let's look at the steps that you are needed to follow in order to write the actual net ionic equations. So we have about 3 steps. Step 1, that is to construct a balanced chemical equation. So usually they will give you an equation. What you just need to do is to inspect. Step 2, you are supposed to write the full ionic equation by splitting. So splitting here, we are referring to dissociation. Then step 3, you are supposed to cancel out what we call the spectator ions. And then finally, you write whatever remains in the equation without those that you've cancelled out, and you are done. Now, to understand this one, let me use 2 or 3 examples. If we go through those examples, I can assure you, you will never fail to ionize any equation no matter what. So let's dive right into it. Worked example 1. It is saying write an ionic equation for the following reaction. So the reaction is copper carbonate reacting with hydrochloric acid, giving us copper chloride, water, and carbon dioxide. So step 1, we are supposed to inspect for balancing. So you are supposed to check how many copper do we have on the left hand side, how many copper do we have on the right hand side. So you need to have the knowledge about balancing of chemical equations. The idea and the purpose of inspecting for balancing is if the equation is not balanced, then you cannot ionize it. So you can only ionize an equation that is balanced. So if we check this one, you find that copper here is 1. We have 1 copper this side. We have 1 carbon. We also have 1 carbon this side. So oxygens, we have 3. Even this side, we have 3. 2 plus 1, so that is 3. We have 2 hydrogen. We have 2 hydrogens here. Then 2 chlorines. We also have 2 chlorines. So this equation is self-balanced. Now, can I just make mention this? These equations, I balance them myself. So never, ever should you assume that an equation is self-balanced. You actually have to balance it yourself. So that is the first step. Inspect for balancing. It's either it's self-balanced or you need to balance it. After you balance it, then you go to step 2. That is where now you have to ionize, meaning dissociate them. So for example, this copper carbonate here, it has got solid. So we're going to leave it alone. It cannot be split. But our HCl here has got AQ. So we can begin by splitting this one. Now, when we split HCl, you know that we're going to have the H and then the Cl. But look at the 2. The 2 in front here, it is in front, meaning it belongs to both H and Cl. So as we are splitting this one, we're going to write the valence, which is 1, and we know that hydrogen is a metal, so it's going to just be plus. We ignore the 1. The Cl also is going to be negative. We ignore the 1. But don't forget this 2. When the 2 is in front, it means it belongs to both H and Cl. Hence, when writing in the equation, this part that is here, it is going to be converted into this part that is here after splitting. So 2H plus, then the 2 will follow because the 2 belongs to H. The 2 will also belong to the Cl. So you write it like that. Then check on the right hand side. On the right hand side, the copper chloride, it is AQ. So even this guy here, we are supposed to split it. So you're going to write your copper and your Cl. Now, the fact that copper here, copper is a transition element, so you cannot really tell its valence unless you use the formula in which it is combining. So here, the fact that we know that chlorine has got a valence of 1, but there is a 2 here, it tells us that the 2 belongs to copper, because remember how we write chemical formulas. There is that part where we swap valences, and since we are sure that chlorine has got a valence of 1, and we are sure that it has got a valence of 1, it means these 2 only came to chlorine as a result of swapping. So meaning the copper here is going to have 2, and then this one will have a valence of 2. Now, you put a plus to the metal, and then you put a minus to the non-metal. Now, remember what we said, 2 here is also being written as a subscript. So subscripts are supposed to be moved in front of that particular species which they are attached. So you don't move it to the front of copper, but you just move it to the front of chlorine, because it only belongs to what? Chlorine. So this 2 is going to move in front of chlorine. Ignore this 1 here so that it remains negative, and that is how you come up with what? With this one here. And then after you do that, you look for H2O. H2O is liquid, so this is not aqueous. It can split. We leave it alone. Carbon dioxide is gas, which is not aqueous, so we are also going to leave it alone. After we ionize, now we can cancel out the spectator ions. So step 2 and 3 can actually be done together. If you are writing in the exam, you don't need to waste space. You can do it. So after ionizing, then you are going to cancel out what we call the spectator ions. So just listen to this one. Spectator ions are simply ions that are found in exactly the same way on both sides of the equation. So if the way it is, let's say if you have 2 on the left hand, even on the right hand you have 2. So 2 is exactly 2. So you cancel it out. It means it did not participate in the reaction. Hence, it has to be cancelled out. So please, I'm going to repeat that again to make it twice. Spectator ions are ions that are found on both sides of the equation exactly the same way. Not similar, but exactly the same way. Why are they found exactly the same way? They are found exactly the same way because they do not participate in the reaction. They are just idle. And we don't want anything that is idle. We need to remove it out of the equation. That's why we cancel it. Because if you put something into a reaction, it has to come out different. If you put the dough into the oven, you expect to get a cake, a scone, or anything. But if the dough comes out as dough, then it means the dough is useless. So that's why it has to be thrown out. That is the same concept that we are using even for spectator ions. So please, before you get lost, we are just trying to cancel out the spectator ions. So here, we are going to look at copper carbonate. Do we have anything that is CuCO3 without being exactly like that? We don't have here. Let's look at the H+. 2H plus AQ. Do we have any 2H plus AQ here? No, we don't. Some people want to confuse. No, it's H plus, so we have the H in the water. No, leave it. I did not say similar. We are saying exactly the same way, not similar. So the fact that there is no 2H plus AQ, it means this one is a useful ion. It's not spectator. Let's look at 2Cl minus AQ. So 2Cl minus AQ, we also have 2Cl minus AQ on the right hand side. So these are exactly the same. So we can cancel out this and cancel out this. So we have removed these. These are the spectator ions. After removing the spectator ions, then we can write whatever remains. So you can see we've removed the 2Cl here. We have only remained with CuCO3, 2H plus AQ. Then even this side also we've removed this one. Only these are remaining. So this one is now the net ionic equation. That is how we write net ionic equation. And please check through, make sure that it makes sense. Okay, let's look at another example. In here, we are supposed to write an ionic equation of the following reaction. So, like I mentioned, for me, I already balanced the equations. So step 1, you are supposed to inspect, but I'm telling you I already balanced. However, never ever assume that it is self-balanced. Check it. If it's not balanced, balance it. After that, then you proceed now to where you're supposed to dissociate. That is where we are saying ionize, is to dissociate. So you check here. Barium nitrate here has got AQ. So this one we are supposed to dissociate. So barium nitrate, if we are dissociating it now, take note that barium is in group 2, just like we did there. Barium is in group 2 with a valence of 2. The nitrate is a radical, so NO3, and we know it has a valence of 1. So, and it has a negative charge. Then barium is a metal, so it's going to have a positive charge. Again, look out for subscript. So 2 is a subscript here. So this subscript here is going to move in front of the nitrate, not in front of everything. It is just in front of that particular species which it is attached to. So the 2 will just move in front of this one here. Let's look at sodium sulfate. It also has AQ, so we are supposed to split this one. So we have the sodium here, and then we have the sulfate here. Now remember, radicals are not supposed to be tampered with. So sodium has got a valence of 1, sulfate has got a valence of 2. So this one will be plus, and then you add a negative here. Now let's look out for any subscript. So I can see a 2 is a subscript here, so it is going to move in front of the sodium, so that we have a 2 here. Please, 4 is not a subscript. 4 is part and parcel of the formula sulfate. So it's not a subscript because it is part and parcel of this radical. Please never confuse those things. So this is how we are going to ionize this one. Barium sulfate here has got a solid. So this one, we don't split it. We don't dissociate. We leave it the way it is. Let's look at the sodium nitrate here. Sodium nitrate also, we have Na on one end, then we have the nitrate on the other end. Now the 2 is in front, which means it belongs to both sodium and nitrate. So we write the valence here 1 and the valence here 1, then metal plus, then non-metal minus. So that is how we are going to split these things as shown in this equation. After you do that, then you're going to look out for spectator ions, those that are found in exactly the same way on both the left-hand side and the right-hand side. So let's look at Ba2+. So here, a negative, okay? Make sure you put the symbols appropriately. So Ba2+, we don't have any Ba2+ here. This guy and this guy here, they are different ones. So spectator ions are supposed to be exactly the same one. Okay. Let's check 2NO3. Then we also have 2NO3. So this guy here, we cancel it out with this one here. It goes. Do we have 2Na plus? So we have 2Na plus and 2Na plus. So this guy here is supposed to go out with this guy here. Let's look at the SO4 2 minus. We don't have any SO4 2 minus here. So as a result, what we're going to remain with is Ba2 plus SO4 2 minus AQ is equals to this one. Now, this one makes sense. When we get barium and sulfate added together, are we not going to come up with this one? So your ionic equation, the net ionic equation, should actually make sense. All right, my YouTube followers, let's just look at one more example quickly, and I think you are ready to ionize any equation that you encounter in your chemistry journey. So this one, we are supposed to ionize sodium hydroxide, reacting with hydrochloric acid to give us sodium chloride and water. So inspect for balancing. This guy is already balanced. Then we have to ionize. So this one, we've done this before. Sodium and OH will ionize into Na plus and OH minus, and then the HCl into H plus and Cl minus. Then, so because this is aqueous, so this is aqueous, it can ionize. Even this one is aqueous, we are supposed to ionize. But the H2O is liquid, so let's leave it alone. So only AQ compounds are supposed to be split. So after that, then we look out for those that are the same. So we can see Na plus here, we also have Na plus here. I can see we have, let me see, Cl minus, also Cl minus here. And when we cancel those out, what we're going to remain with, okay, we cancel those out, what we're going to remain with is OH plus H and this will give us the H2O, which has remained here, of which this net ionic equation also makes sense. So that is how you balance, that is how you write the net ionic equations. This is just the summary of the steps that we've been looking at. You can pause the video and just go through the steps. Google any other ionic equations on YouTube or on Google and just try them out on your own. Thank you for watching this video. Please like the video and do give us feedback in the comment section. Thank you.